Hi all, we will start with a common enough situation that we've seen in this class before. We have a ball and the Earth is at a position H, and the ball starts off at a position H plus little h, so that the difference between these two is little h. We will say that gravity G is downwards. We will say that the positive direction is upwards, and just for the sake of this example, we will say that the velocity of the object is initially downwards and positive, so it's not starting at rest. We can write our kinematic equation as 2a delta x, and we can remember that the kinetic energy of a particle is defined as 1/2 mv squared. So we'll multiply both sides by 1/2 mv, 1/2 m. So we get 1/2 mv squared equals 1/2 mvi squared plus ma delta x. But in this case, our acceleration will be g, and it will be negative. So that's negative g. So now we're going to get our kinetic energy final equals our kinetic energy initial minus mg delta x. So now we need to calculate our delta x. So our delta x is, remember, x final minus x initial. So this particle ends at big H and starts at minus h plus little h. So if we now use that, we'll get this minus mg big H minus big H plus little h. We can distribute that in. We can pull the kinetic energy to the other side, so that we get delta Ke equals minus mg big H minus big H plus little h. We can multiply this in. So we'll get delta Ke equals minus mg big H minus mg h big H plus little h. Sorry, that went off the screen. So we'll have delta Ke equal to, and what we can do is we can see, since by multiplying by 1/2 the mass, we ended up getting energy. We can define the gravitational energy, Ug, near the surface of the Earth as the mass of the object times gravity times the distance above wherever you're referencing to, the potential energy. So this mgh is the final potential energy, and then this h plus big H is the initial, so the negatives will cancel and we'll get plus ui. So this is really ui minus uf, which is equal to minus the change in potential energy, and that's equal to the change of the kinetic energy. So one thing that's worth remembering is the change in kinetic energy is equal to minus the change in potential energy for a conservative force. So how do you know if something is a conservative force? So things such as gravity and electricity are conservative forces, and the way we know that is because they have field lines which begin and end on objects. So gravitational field lines end on masses and begin at infinity. Electric field lines end on negative charges, or at infinity begin at positive charges, or at infinity, so those are conservative. Things like friction will not be a conservative force. So this is something we ended up with. The change in kinetic energy equals the negative change of the potential energy. We can write this out again, so we'll get Ke final minus Ke initial equals minus U final plus U initial. If we get the finals on one side and the initials on the other, we'll have Ke final plus U final equals Ki initial plus Ui initial. And what this says is that the energy afterwards equals the energy before, or the the initial energy equals the final energy, so this is called the conservation of energy, meaning if something is governed purely by conservative forces, then the mechanical energy, which is the sum of the kinetic and the potential energy, is equal to 0. So we would like to define the work that an object does as the force, the net force acting on that object, dotted into the distance of the object. So say we have some distance here d, we have a force here F, there's some angle theta in between them, then the amount of work done is equal to the magnitude of the force, the magnitude of the distance, the cosine of the angle between them. So if these are at 90 degrees, then no work is done, and if they're purely parallel, so if the force and the distance are in entirely the same direction, then it's just F times d. This can also be written as the x component of the force times the x component of the distance plus the y component of the force plus the y component of the distance plus the z component of the force times the z component of the distance. So work is a scalar quantity, meaning that it is of the same units as energy. Work will end up having positive or negative signs, and that is only because work has to be defined either as a force doing work on something or the work done on an object. So in the previous situation, we could look at having the ball starting at the ground and trying to go up a height h. So remember that the gravitational field lines G all point downwards. Now the force due to gravity, so let's look at the work done. Force due to gravity, if we say x is positive, going upwards, the force due to gravity will be minus mg. And since, okay, let's redo this. The force due to gravity is mg. The distance will be big H. And if we have distance going upwards and the force going downwards, so that's distance and that's the force gravity, then the angle here is 180 degrees. So the cosine of 180 degrees, that's negative, so the work done is equal to minus mgh. Now what does this minus mean? The convention is that if the field is doing work, so causing the object to move, then the work is positive, and if you have to do work, then it's negative. So this is saying that you had to do work to get the object from the ground upwards. So this is saying that it's much easier, you have to do work to climb stairs, whereas it's much easier to fall down them. Now if we remember that this was h and then this was h plus little h, then we can compare this to the change in potential energy. So the change in potential energy from going to here upwards is mg big H minus mg, okay, so that was big H, sorry, so let's be consistent. This is little h now. Sorry, it flopped. Little h, little h. This will be h plus little h. And then this one is little h. So this will end up being equal to minus mgh, which was the work that we had done. So we see that the initial minus the final is equal, so this is the u initial, this is the u final, so we see minus the change in potential energy is equal to the work done, and this is only for conservative forces. That's what the C is for conservative. If we remember from before, the change in the kinetic energy is equal to the negative of the change in the potential energy. So we can also say that the work done for a conservative force is equal to the change in kinetic energy of the object. So this one will hold only for conservative forces, and it will turn out that this one is generally true. So how do we see that? Say we have an object that starts off at rest, mass m, it gets pulled by a force F. And later, the object now has a velocity v, still has the mass m, it's got the force F acting on it, and it traveled some distance d. So if we look at the Vf squared equal to Vi squared plus 2a delta x multiplied by 1/2 m, so we'll get Ke final equals Ke initial plus ma delta x. So in this case, the ma will be our net force. Well, it was always the net force, it's just at this point the net force we're going to ignore friction is just this F here. So our change in kinetic energy is going to equal to our force times the distance that it travels. But if you remember, this is just how we define the work. So even in a non-conservative case, the change in kinetic energy is equal to the work. All right, thank you very much.